Hello, welcome back to another video. Today we are going to start with the Computer Science Foundation. Um, Before we start, there is some concepts that we need to know and we need to understand them in order to go on. But before all, I would like to say, check here, abstraction, okay? Because for now, we will see some materials and we will see the definition of them, and we will try to get some concepts. But as the project go on, it will force us to go deeper and deeper until we almost find the root for those concepts and in certain scenarios. So it's something that we will see in the future, because if we try to find the root for every single concept right now, maybe we will not get it, or it will take us long, like I'm talking about years, until we can just, for example, to carry on with the next Python course or with some maths, which will be the next material to do. So for now, as we are learning, let's go with abstraction. Okay. Okay, so the main goal of this video will be to understand what a computer really is and why every digital system has a physical world, like matter, energy, charge, voltage, current, resistance, heat, signals, data, rules, states, and output. Okay, and I will leave this in here also with this core part, which is reality, signal, data, rule, state, and output. Okay, this will always be done in computation, but we will talk about this later. Okay, there is many concepts, so let's try to get it done fast as possible. The way that I will do in your case, if you want to follow the class and if you are really into the project and you want to learn what we're learning, I will suggest just take a notebook and just jot down every single definition and try to get it. That's the way that I'm doing it. I just get all the definitions and I just read through them a million times until I get it. Because if we don't get the foundations, we cannot carry on. But let's try to make it like really simple. Okay, we can start. As we say here, computer is a physical system that really is an okay. Yeah, never mind. I thought I have the definition of a computer in here, but no. Okay, so we're gonna start with computer. Is a physical system. I'm gonna get like this. Is a physical system organized to transform signals into useful information and output. So it's kind of difficult to write in here. I will get it like better with the time. So computer is a physical system organized that transforms signals into useful information and output. So we have, for example, here we can put real world. Okay. Real world. Okay. This is a computer. So you need to mentalize that every time I do this, I'm drawing a computer. Okay. And output. So we said that a computer is a physical system organized to transform signals. This is a signal, transform signal into useful information and output. Okay, let's try to get down all the concepts. So we can say physical system, physical system. We can say that a computer belongs to material reality. Okay, like matter, electricity, wiring, heat, noise, and physical limits. Okay, we have, for example, electricity, we have heat. So we can say that a computer belongs to material realities like matter, electricity, heat, and physical limits. Okay, very basics for now. Okay, we move on and we can say input. Input is what enters the system from the outside. As a signal, command, or measurable event. Okay, an input is what enters the system from the outside as a signal, command, or measurable event. Okay, for example, okay, a key press, for example, right, which is could be, for example, F or L, M, any key from the keyboard. That will be the input, right? It will be an input that goes to the computer, right? And we can say the before processing something must enter the system. Okay, we can say sensors. What is a sensor? A sensor detects a physical variation and converts it into signal. Or value. Let's say value the system can use. Okay, detect a physical variation and converts it into signal value or value the system can use. For example, heat light or sound is captured by a sensor. And it could be, for example, a 42. Because of the heat, it could be 42 degrees. So it's something that is captured by a sensor, and the sensor transforming into value or something that the system can use. Okay? So we can say, just to make it clear, that heat, light, and sound could be also pressure, and sound also say here, only become usable values through sensors. Okay? There are so many concepts, basics that we need to know. So I'm trying to make it like fast so the video will not be 2 hours long. We have signal. A signal is a measurable event. Oh, sorry. Physical variation such as light, temperature, pressure, or voltage. Okay, so we have light, sound, temperature, pressure, and all of them are measurable physical variation. Okay, and we can represent the physical variation with this sign. Okay, so we can check here. Okay, let's see data. Data is a representation of reality. This is a representation of reality, but let's put a different definition and we will see that definition later and explain it later. We can say for now that data is a representation of a signal or event in a form the computer can store, compare, and process. Okay, so we have example, this is a signal. Data can be 42 and it will be stored. And we can see that data is useful. Oh, did I change color? But it is not the physical thing itself. Okay, so data is useful, but it's not the physical thing itself. It's a representation of the reality, not the reality itself. That's what it means. Okay. And we can see more or less here is the same representation. Is the way reality is encoded inside the system. As numbers, bits, symbols, or stored values. Okay, we have a real object it will produce a signal, and the signal can be stored as values. Okay, and we can also say that the representation is not the thing itself. The computer handles representation. Not reality directly. Okay? We can say digital means physical states are organized into stable. Distinguishable categories such as low, high, or 0 and 1. We will also see that later, but for example, low can be represented 0 and high can be represented as 1. That's why digital means physical states are organized into stable, distinguishable categories such as low, high, 0 and 1. We can say the digital does not remove the physical. It organizes it. Okay, because for example, this can be like voltage, right? And the voltage can be low, can be high, and this is a physical variation that will be digital in here. But this digital is not changing because one this is coming as an output and it's coming like for example one is the output. It doesn't change the physical variation of this. It means that it's high, that the voltage is high, so the high voltage will be sent and stored as 1, and then 1 will be the output of 1, and 1 means this high voltage. So digital doesn't remove the physical is still here, it just organized, because if it's 0 it will be low. So it doesn't, the digital doesn't change the physical, it just organizes it. Okay. we can be the difference between analog and digital. Analog changes continuously. Digital organized values into discrete states that can be stored and processed reliably. Okay, so we have, for example, this is analog because it's a continuously variation, and this, for example, is digital. This is a discrete state. And we can say that a wave can vary smoothly and a digital system forces stable categories. Okay, more or less we get the difference between analog and digital. Let's say rule instruction. A rule is an instruction or condition that tells the system what to do with data. So we have data could be 42. If greater than 40, then print an alert. So a rule is an instruction or condition that tells the system what to do with data. So we have a data which is 42, and then it says, hey, if the data is greater than 40, then print, for example, alert or activate alert. We're gonna see processing. Which means applying rules, operations, or models to data in order to produce new data. Or an output. So we have the data, CPU, and it gives new data or an output. So processing is equal to applying rules to data. And we can also say that processing is not human understanding. It is rule-based transformation. Okay. It's a memory state. Memory state. Memory stores information. So the system can preserve and continue a process over time. So we have, for example, past data, then it goes to memory, then it gives a state. We can say the memory keeps continuity. Without memory, the system loses continuity. Okay, we have a past data, which could be, for example, the example as we saw before, 42 degrees. And then we have a process in here which say, okay, if the data is greater than 40, then print alert, right? For example. Okay, then we have a data, and imagine that we don't have memory. Okay, and then we reach to that point. If data is greater than 40, print alert. Okay, I can do that, but where is the data? If we don't have memory, how can I know the past data? For that reason, without memory, the system loses continuity. We need that memory to store the data, and then we go on. Let's see output. Output is the result produced by the system which could be an image, sound, file, command, network reply, or decision. So we have the CPU, and then it could be an image, file, network, or sound. Then we can say that the output is where internal processing becomes visible or actionable, right? Which could be an image, file, network, or some. If you double click on an image, then as an output you got an image, and the processing of double clicking the image, the images would become visible or actionable. Okay. Then we have this core path, which is this chain is okay. Let's try to put this is the base of causal chain of computing. Okay, so this is the base of causal chains of computing. This chain here, this will always be followed. Without this, there is no computing. Because we can say that a real system always follow wall, something physical variation from the outside in the wall will be captured by a sensor, and then the sensor will make data, and data will be applied by a rule or a model, and then it will give an output or an action. So always the same process will be followed, and we can say that this connects Computer Science Foundation to sensors, robots, AI, and maybe in the future, hopefully, a suit. Okay. Okay, I think the writing is good. We can move on because I want to do two modules, module 1 and module 2. Module 1 it covers the basics, as it says here in the goal, understand what a computer really is and why every digital system has a physical root. And now let's do abstraction on those physical roots. So for example, we have matter. Okay, the matter is the physical base of the computer. No digital system exists without real materials. Okay, we can try this. We can try to interpret the CPU, and from CPU the computer. So we can say the digital world is built on matter. Okay. erase it. Okay, let's check atom. Is a basic unit of matter. For now we'll say here abstraction. Okay, we will hopefully in the future we will see it more deep and deep. For now, all we need to know is the basic unit of matter. If we try to represent it, we can do like, and we can say that the matter has internal structure. Okay, let's move on. Electric charge is a property of matter that allows electrical interactions and supports signals and circuits. Okay, let's try to represent it. Okay, this is an electrical interaction. And charge is is one physical reason circuits and signal exist. Okay. Let's see, electric field is a region of electrical influence around charge that helps explain how electrical effects act in space. Okay, we can represent it. That could be like an electric field, and we can see the field. This is the field, which is a region of influence. And then the field is not a wire. The field is not a wire, it's a region of influence. Okay? So is a region of influence. Let's see energy. Is the capacity to produce change. Every signal change. Memory state and process depends on energy. Okay, so we have energy and a change. If there is no change, there is no computation. If a system changes state, then energy is involved. Okay. Let's check voltage, and we can say that is the difference in electrical potential between 2 points. And it creates the possibility for charge to move. So we can say high and B could be low. Voltage is equal to different. So voltage, we can say the is the different, but not the movement itself, because it's very important not to confuse the voltage with current, because we can say the voltage is different, but current is the movement. Okay. Now we also have the definition of current here. Current is the ordered movement of electric charge. through a path. Okay, so we can say that current is equal to charge moving. So current is the movement itself. Let's see, resistance is the opposition to the movement of charge. In real system, part of the energy is transformed into heat. Okay? So, for example, this could be heat. In here, this is heat. This is an opposition to the movement. And resistance creates losses, and losses often becomes heat. That's why this creator resistance is an opposition of the movement, that the movement is going straight, right? And there is something here that opposite to that direction, and this energy that is involved in here, it produces heat. That's resistance. Let's say heat. Heat is energy dispersed through losses, and it is one of the main physical limits of computation. Okay, this is heat, and losses become heat. In real machine, need cooling because computation is physical. Okay, so this is heat. Okay, so we can physical state is a sensible condition of a system, such as high, low, on or off, charged or not charged. Here we can say that off or low could be represented as 0, and on and high could be represented as 1. Now we can say that a bit needs hardware states that can be distinguished. We have the bit. Bit is the smallest unit of a digital information, and usually represented as 0 or 1 based on distinguishable physical states. So we have a physical state can be 0 or 1, and that is a bit. And we can see that a bit is not magic. It rests on physical states. Computation is equal to physics. Computation is not separate from physics. Every operation depends on matter, energy, electrical behavior, and real limits. Yeah, so we can say here matter, energy, states, bits, and computation. And we can say that this is not, as I want to write anymore. That this is the deep foundations of computer sensors, robots, and AI. And basically, this all these concepts, well, we have to read through them like a million times, and this is like very abstract. We did like a really abstraction into that because on the future on this project we will go back to these concepts and definitions and obviously more deeper and deeper into it. So for now this is really abstract, and this is something that it will be really good if we start to get to know them in order to carry on. Otherwise, if we don't really build solid foundations, then it could lead to real problems later, right? So just know them, read them a million times, and then you'll get it. It's just a matter of time.